Useful. So year 13 work, this is what we're starting. P17.1, and it is motion in a circle. And you should be able to access Caboodle for this P17 work because it is the year 2 book. So right at the start of the year 2 book. So we're talking about things that have motion in a circle. So I wonder if anyone can give me some suggestions about what moves in a circle. What has what we would call uniform circular motion. Have we got any examples of things that are going to have uniform circular motion?
Swing ball.
A swing ball that's at a constant height. Yeah, I'll let you have that one. Try and think of simpler ones. I'll give you an easy one.
Ceiling fan.
Ceiling fan. Oh, that's a good one. I hadn't thought of that one. Ceiling fan. Yeah.
Train going around tracks, but the tracks are arranged in a good circle.
That's the terrible one, Jay. What about a record? Record player or CD player. What else? Something else that goes around in a circle.
A washing machine.
Yeah, that's a good one. Yeah, I didn't think of that one myself. That's a very good one. So a washing machine, that's uniform circular motion whilst it's on. Any others?
Use my head around.
What about wheel?
Oh yeah.
Wheel on a car, wheel on a bicycle.
What if the wheel's not true though, and it goes bumpy?
A satellite around the Earth, or even the Earth around the Sun. What about the solar system around the galaxy?
I thought those are all eclipses, weren't they?
No, they're all circular motion. They're things moving in a circle. All right, maybe they're things moving in a circle when we consider them as a simplistic system. When we go too complicated, obviously they're ellipses. But as far as we're concerned, they're circles. What about? And there's two more I'm going to give you. A plane doing a loop-the-loop. That's circular motion, especially if it does it repeatedly. And the last one, because we're going to use this one later on in the topic, about a roller coaster. At what point would a roller coaster be doing circular motion? Uniform circular motion.
The loop as well.
Yeah, loop the loop. Might not be a perfect circle, but it is following circular motion. Okay, so this is what we're talking about. We're talking about all of those different examples of circular motion, and there are many, many, many more. You'll think of more as you're doing this topic, like the London Eye. That's uniform circular motion, and trying to think of any others. There are loads out there. I'll let you discover them. But what do I mean by it? Well, I mean that something is moving in a circle uniformly and in motion. I mean that is simplistically it. So let's consider a wheel. It's going to be an old school wheel that's got spokes on it. Okay, so there's a wheel. If I want to go, my wheel is rotating from that point, use some different colours, all the way around to that point in a circle. I mean, that's not great, but it will do. How far is it going to travel?
It's going to travel the circumference of the wheel.
Okay, circumference of the wheel. And what's the circumference?
Pi times diameter.
Oh, I don't like diameter. Come on, give me better than that.
Pi 2r.
2 pi r.
Yeah.
There's a reason I write it that way, and we'll come across that later on, because this 2 pi is really important. Okay, so 2 pi times by the radius. And if the time it takes for it to rotate is t, then surely we can say that the speed of rotation, and obviously we'll have better symbols for this later on, is going to be 2 pi r divided by t, because it's the distance divided by the time taken. Do we know anything about 1 over t?
That's a time period.
It's a time period. What's 1
Yeah,
over
that's
t equal to? 1 over the time
t
period.
to the -1.
It is t to the -1. Frequency. So therefore, we can say that my velocity is 2 pi r multiplied by f. Frequency, so how many times per second it's revolving around. 2 pi, which is to do with the angle in radians, which we'll come to a bit later on. And the radius, because that's also to do with the angle in radians, but this part gives us the distance it travels and how many times you do it per second. 2 pi rf. So let's have an example. Let's do a very simple question just to start us off with this one. And we'll start with passengers in a fairground ride. Okay, so one of those rides that you can go to the park when they're open and sit on and they spin round. Okay, are 4 meters from the rotational axis. What do I mean by rotational axis?
The pivot in which it rotates around.
Yeah. So the ride rotates once every 12 seconds. So we've got 12 seconds for it to rotate. So what kind of ride am I thinking about? I'm talking about a ride that looks a bit like this. It has, as you say, a pivot in the center that it's pivoting around. Okay, so the ride is moving around in a circle. Here are the people in the center. And there is the 4 meters distance from that rotational axis to where the person is. Okay, really schematic drawing there. But anyway, it gives you an idea. So first of all, let's work out the frequency of rotation. So frequency would be 1 over the time period for one rotation. Well, that is in fact going to be 1 over 12, which is going to be, work this bit out on my calculation, 0.083. And what would be my units for that? Frequency. Anyone want to hazard a guess? We've used frequency before with waves. It's exactly the same. It's hertz. Okay, and this is going to be really important because later on in this topic, we are going to relate circular motion to waves. Okay, it gets a bit more complicated when we get to that, simple harmonic motion, but we will get there. But for the moment, frequency, hertz, and frequency is 1 over the time. So we want to know, I didn't ask what my question was, did I? What's the speed? That'll be quite useful. What's the speed that this person is moving at? Well, velocity is 2 pi r multiplied by f. So that is 2 pi multiplied by 4 multiplied by 0.083 or 1 over 12, which if I do the answer gives me 2.09 meters per second. So that person there is going to move at 2.09 meters per second. What's going to happen if I increase the radius? To carry on rotating at 0.083 hertz, so 0.083 times per second. What's going to happen if R gets bigger? What do we think? Any ideas, guys?
The speed gets bigger?
Yeah, speed's going to get bigger. And we know that because when we did satellites last year in your GCSE, in order to move a satellite to a greater orbit, you had to increase its speed. And if you slowed its speed down, what happens to a satellite? Well, it comes back in closer. And if you slow it down enough, then the satellite will collapse into the Earth. So to get it rotating, because it's got a greater distance to travel, displacement to travel. So if I was to draw that, I don't know, let's say 8 meters away, then my disk would look like this and my person be further away, but the distance it has to travel going round in a circle is greater, so therefore your speed must be greater. Okay, good. I hope that makes sense. Any questions? Perfect. Don't forget, you can use the hands up button. I've never seen what happens when you press the hands up button. If you want to ask a question, and then we can come back to it. I have got Teams open in the background, so I can see. Right, so let's use some terminology here. Angular displacement and now I'm going to call it speed for the moment, but realistically it should be velocity, but let's stick with speed. So angular displacement and speed. Right, it's going to be a terrible drawing now. Oh, actually, let me just see if I can find my animation. I always use an animation for this. And if I can find it, that would be better than giving you a terrible drawing. Circular motion. Have you learned about radians in your maths class? Can I presume not? Here we go. This is the one I want. So if I do that in a window. One second, we'll be there. Okay, so I'm just going to share this with you instead, which is the PowerPoint. I'm going to make it start again. So here we can see what a radian is. So it's a measurement of an angle. Okay, and we can see that we just transcribed a full circumference there, but we've taken a radius and we're now mapping it onto that circumference. And the angle that you have that is equal to the sorry, let me get this right. So 1 radian is the angle that is equal to the distance subtended around a circle that's equal to the radius. And there are pi radiuses subtended around half of a circle. So watch that again, because I think this is really important to see. So stretch out the radius, transcribe that circle, take the radius, and we're going to subtend it to the circle itself. So we're going to overlay it. That angle there is 1 radian. And if we look really closely, you're going to see that you get 3 and a little bit in half a circle, which is then pi. And so 2 lots of that is 2 pi. And if we multiply that by its radius, then we're getting the circumference. This is where the circumference comes from. And it also explains what a radian is. So 1 radian. Okay, and the symbol for radian is rad, but you may also see it as not a circle like degrees, but a C. Okay, so 1 radian is the angle given by an arc of length r around a circle. So let's try and draw that for you so you can see it. So there is our length. It's probably a bit too long. Let's cut that back a bit. Oh, too far. Never mind. So that length there would be r, and that length there would also be r. So this angle here, which we'll call theta for the moment, so theta will be equal to 1 radian. Okay, so if there's 2 pi, so one whole circle, so let's say 360 degrees is equal to 2 pi radians. So let's work out what 1 radian is in degrees. Well, 1 radian, 1 divided by the total, divided by 2 pi, multiplied by 360 will give us our answer in in degrees, sorry. So 1 radian will be 57.3 degrees. Approximately. I'm going to put a little approximate sign over that because obviously, because we're using pi, it's a never-ending number. It's an irrational number. So therefore, we will have a long set of decimal places on that as well. So that's the way to convert from radians. So you want the number of radians you've got divided by the total radians in a circle multiplied by the number of degrees in a circle. So we're doing a ratio multiplied by degrees. What about if we want to go the other way? Let's say I've got 90 degrees. So 90 degrees is going to be divided by 360 because that's my ratio of my circle, multiplied by what I want to turn it into, 2 pi because I'm radians. So I'm going to be 90 divided by 360, multiply that by 2 pi. And if you do that on your calculator, you will actually find it's left in pi. So it's 1 over 2 pi, which is a half of a pi. And if you want that as a number, then that'd be 1.57 radians. Okay, so that is what we're talking about here when we talk about radians. So what about angular displacement? Is that all right if I rub this out? Oh, I haven't. Sorry, you've still been having the slideshow. Well, that was no use. Let me. Joe, you've got a hand up.
Oh, no, sorry, I was stretching.
Thank you, Joe. Sorry, let me move back to the visualizer. So you were listening to me, but you couldn't see what I was writing. So here it is. So 1 radian, rad, is the angle given by an arc of length r around the circle. So here we've got a slice of our circle. The arc's length is r, the radius is r. So this angle theta is 1 radian. Now we know that 360 degrees, a full circle, is 2 pi radians, because that's what we've seen when we look at that diagram, and we know there's 2 pi around it. So 1 over 2 pi times by 360, there's my ratio of what I've got in terms of radians, multiplied by my number of degrees in a circle will give me my answer in degrees. And there's my ratio of my degrees multiplied by the number you get in a circle in terms of radians, which gives me my answer of 1 over 2 pi, which is 1.57 radians. Okay, my apologies that wasn't up as I was doing it. I'll leave that for a moment. We're not far from the end of this one, guys, so don't worry too much. Everyone happy for me to rub out? Okay. So we've talked about what a radian is. So let's deal with so any object then. So anything in uniform circular motion will move or moves through two pi over t radians per second. Because in other words, it can move in one whole circle, it will move 2 pi radians, and the amount of time it has will tell you how many radians per second it's going to move. So let's now deal with angular displacement. So angular displacement is going to be called theta. So if it moves a certain number of radians in a certain amount of time, then we can say that theta is going to be equal to my 2 pi divided by t, which is how many radians it does per second, but we want it in radians, so I'm going to multiply it by the amount of time you have. So in other words, you're looking at the ratio of the total time multiplied by how many radians you have. So if that is greater than that one, so if t is greater than that one, then you're going to have more than 2 pi. If little t is smaller than big T, you're going to have less than 2 pi, which means you've not done a full revolution. Okay. And we also know that 1 over T is equal to the frequency. So we could also have 2 pi ft. So that's an important equation. In fact, let's box it. Those are both very important equations that you're expected to know and use. And we'll do an example of those in a moment. But let's do one more. We're going to do angular speed. So if that's angular displacement, angular speed. Now this does have a special symbol, which is called omega, which is like a curly W. Okay. And angular speed is going to be angular displacement divided by time. I'm not going to fit this in, so let's get rid of this top bit. We'll just start again. So angular speed, let's write a bit quicker. We'll call omega. So angular speed is going to be angular displacement divided by the time, which in our case is going to be theta divided by t. Well, angular displacement we've just learnt is 2 pi t divided by big T. We're dividing that by time, little t. So in fact, that is going to mean that that one can come up to here, and then the t's are going to cancel. So we're going to be left with 2 pi over big T. We also know that 1 over big T, 1 over the time period, frequency is okay. Thanks, Joe. So second.
Sorry.
That's all right, don't worry. Second equation is there, which is 2 pi f, which gives us our angular speed. So that's how many radians per second we have. Okay, so this would be rad s to the -1. Okay, so that's it. That's the theory for the lesson. I want to do a few. In fact, I want to just do one example with you now. 3 parts of this example, and then you have got your questions to go and have a go at, and I'd also like you to have a go at the summary questions as well, but we'll go through that in a moment. So I'll rub this out. Again, remember, I will upload the video. I'll either put it on YouTube or I will upload it to Teams. So we have, here's our example, a car, wheel of radius, it's a big wheel here, 0.4 meters, rotates once every going to change what I've written, 0.25 seconds. Okay. So I want to do 3 things with this. A, we want to determine the frequency of rotation. So we want to be able to work out lowercase f. B, we want to determine the angular displacement in 2.5 seconds. I think 2.5 seconds is too long. Let's change it. Angular displacement in 0.9 seconds. Let's make it horrible. And then C, we want to calculate the angular speed. Right, let's see if we can get this done on one whiteboard. So I'll move it up a little bit for us. So part A. Nice and straightforward, that first one. F equals 1 over the total time period. So that is 1 over 0.25, which, if my memory is correct, will be 4 hertz. So 4 times every second this car is rotating its wheel. Okay, we actually now could work out the actual velocity of it as well. So maybe we'll come back to that at the end. But let's do B now. We want the angular displacement. So the angular displacement, theta, is 2 pi f t. So it's 2 lots of pi multiplied by our 4 hertz multiplied by 0.9 seconds. So that is going to be 2 lots of pi multiplied by 4 multiplied by 0.9, which is going to give us an answer of 22.62 radians per second. So that's how many radians per second we're going to get. And then angular speed, omega, is going to be equal to 2 pi multiplied by f. So that's 4 lots of 2, which is 8. So it's going to be 8 pi. Don't like it left in pi. That's more for maths. So we turn it into a number, 25.13. Oh, no. Sorry, that's going to be 22.6 radians and 25.13 radians per second. So that's radians because that's how many radians it will move through in that time period. This is radians per second because this is how many radians it's doing in 1 second. This, because it's 1 second, should be greater than this because it's 0.9 seconds. And that agrees, 22.62 and 25.13. Okay, right, so that's the end of that question, and that's the end of this lesson. So your activities, and I will put it up as an assignment, I'm going to do that in a moment, but I would like you to do the summary questions from Caboodle. 1 second, let me find my Caboodle book. Just didn't have it open. So you're going to go into the year 2 book now, and I'd like to do the ones on page 5. So it is Caboodle page 5 summary questions. I'd recommend you read it again as well. There's